Hey, pre-calc people, what's good in the hood? We got some sunshine today. It's a beautiful day to do some trigonometry. That's what I always say. Never said that before, but I'm going to start because you know what? I freaking love trig, and I think you guys will like it too. Hopefully my energy is coming off through the walls of my house all the way to wherever you guys are. Friendly reminder, I miss you guys so much. I'm really sad that I don't get to see your guys' face. And also watch you guys learn and watch things tick in your brain and answer questions in real time. But I digress. Let's get on to some trig though. So today we're going to start section 7.2, more on verifying identities. I actually have chosen to break this up into two sections as well, just because after section 7.2, it starts to add on more to our plate. So not only do we already have a ton of things to think about in terms of fundamental identities that we're going to use for verifying statements, but then we're going to add on some more, and then things are going to get really crazy. So before we do that, I know this can be challenging, and also with social distancing and everything like that, I don't want to put too much on your plate. I want you guys to get in some good solid practice because, oh, let me tell you, this stuff ain't easy. I might make it look like it's all fun and dandy, but honestly, sometimes it takes me at least 15 minutes to figure out which identity to use, because quite honestly, I'm rusty. I don't do trig in my free time, despite how much I like it. I do have a life. So when I come back to it, I'm like, oh my God, I love these so much. And my crazy mathematical brain has a lot of fun in the problem solving process, but by no means is it easy for me. Sometimes I can uh, see what needs to be done a little bit quicker than others, but that just comes from years of practice and knowing the identities very well. So today we are going to do half of 7.2, which is just a little bit more on verifying identities, getting you guys some good practice. So today we are going to identify and use identities due to symmetry, something we haven't really discussed yet, but makes sense. Then we're going to just verify general identities. And actually tomorrow I'm going to save using counterexamples to disprove identities until then. A counterexample is a fancy way to say false statement, right? So if you want to know if know if something's true, it can't be true if it's false at least once. So we come up with an example that disproves that statement, and voila, that's all you need to disprove something, which is kind of fun. However, they don't give you any hints on how to disprove. That was the most difficult part for me, honestly, in my math degree, was we would come to a problem and it would just say, or a theorem or corollary, and it would just say prove or disprove, and it would have a statement. And it wouldn't tell you if it was right or if it was wrong. So you kind of had to rack your brain and think about, is this always right? When could this fail? When could I break this law? Under what circumstances would it happen? Or if there wasn't anything that could break it, is this always going to be true? What must I consider? And so that's where things got really, really, really tricky for me, at least. But I've come to love it, you know. Math is a love-hate relationship for me, mostly love, a little bit hate, but it's just because it makes me work hard and it makes me use my brain, and I love that. So let's get into it, shall we? And enough of me just blabbling. Can you tell I miss talking to you guys? I miss seeing you guys every day in class. I miss talking to you guys. I miss watching you guys learn. But you know what? It's a beautiful day outside. The sun is shining. It is not raining anymore. It is a wonderful day to do trig, as I always say. Actually, I've never said that, but I should start because honestly, trig is awesome. Okay, so we started off talking about trig with the unit circle, and we know that the unit circle has symmetry, right? That's the reason why we only need to know values in the first quadrant, because we can just change them in quadrant 2, 3, and 4 because of the symmetry of this circle, right? So it comes as no surprise that the symmetry of the unit circle is going to come back and help us out in times that, as a matter of fact, I think I just made a realization that it comes back and helps us out in calculus as well. I'm not going to go there, but I think I just had another realization that I hadn't thought about in a while. But yeah, so the symmetry of the unit circle is, let's just look at this figure really quick. Let me get my cool little laser pointer. So here's our unit circle, right? This arc is T. That's either like some sort of radian measure, arc length, whatever you want to call it. This is along the x-axis, so that's the x distance. This is the height, that's the y distance, right? Or over here. And normally we would have like a triangle, right? With our unit circle, we would draw a right triangle, drop it down. Here's our 90-degree angle, right? This is our hypotenuse, and we would say x comma y is this point right here where my laser is pointing at, and cosine is x, sine is y, right? And then this is in the positive direction. This is an arc going in the negative direction. So what we didn't realize, and inadvertently, is that the symmetry of the unit circle led us directly to the final group of fundamental trig identities that we talked about last time we were together in section 7.1. But it's going to give us a cool couple identities as well. So given t is greater than 0, so just a positive arc length, consider the points on the unit circle, this point right here, x comma y, with t and negative t in this figure, right? From our definitions, we know that sine of t, sine of this arc length, is going to be y because sine measures the vertical height, right? And sine of negative t going in this direction is going, sine of negative t is going to equal negative y because it's sine is still the y value, right? It's still that vertical distance. But if we think about the fact that sine of positive t equals positive y and sine of negative t equals negative times sine of t, like it's this except flipped with a negative because of that symmetry, we just showed that sine is an odd function. Now, I know I don't even think this semester we've talked about even and odd functions, to be quite honest. But do you guys remember way back in the day when we were determining if a function was even or odd? I'm pretty sure we started talking about it in rational functions, and then polynomials, it tends to come up quite a bit. But we were proving if something was even and odd. Now, you might be like, Ms. Passmore, why do I need to know this now? This makes no sense. But this comes in super clutch when we're doing identities, because sometimes you'll be working through a proof and you'll be like, oh, I'm so close, I'm just off by a negative sign. What this tells us is because of symmetry, and sometimes depending on where the negative is off by, I can use the fact that sine is an odd function to have this negative out here or move this negative on the inside. I can go back and forth between this equality. Sine of a negative t is equal to negative sine of t. That is something that I'm pretty sure at least one example today we're going to come across that. But that's just something to keep like in our back pocket, right? And since the unit circle is symmetrical, and we have our three main trig functions that like work right off that unit circle, well, all six really, because reciprocal functions. This also allows us to find the remaining identities due to symmetry in the exact same way, right? So because sine is an odd function, clearly cosine is going to be an odd function, and then tangent is in terms of sine and cosine, so tangent's going to be defined to be an odd function as well. So the remaining identities are sine of negative t is negative sine of t. Careful with cosine. It's cosine of negative t equals positive cosine. Tangent of negative t is going to be negative tangent t. Now, this is because of quadrants. If you think about where cosine lives, where cosine's positive and negative, that will make a little bit more sense to you. But I mean, even though we have these three core functions, we know that cosecant is the reciprocal of sine. So if sine is odd, then the reciprocal of sine is also going to be odd. So we'll also have cosecant, and we'll have cotangent, and we'll have secant to also be odd. So Here's our big, before we just had our reciprocal identities, our ratio identities, and our Pythagorean identities. Now we're adding into identities because of symmetry as well. So these are all at our disposal while we're working through these problems, right? We've got sine of t is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotangent. The ratios, tangent in terms of sine and cosine, tangent in terms of secant and cosecant, cotangent in terms of cosine and sine. Sine squared plus cosine squared is 1. 1 plus tangent squared is secant squared. Cotangent squared plus 1 is cosecant squared. And now sine of negative t is negative sine of t. Cosine of negative t is cosine t. Tangent of negative t is negative tangent t. So we just added these bad boys in here to our plethora of things. And we are not going to stop adding things to our things that we can manipulate, right? I believe the next section we start talking about, what does it say here? Sum and difference identities when you're adding and subtracting trig functions or sum identities. And then we get into double angle formulas and all kinds of fun stuff. So we'll get to that when the time comes. But let's try an example. Okay, let's use symmetry to verify this identity in specific. So today's problem set is the 3 problems that we're going to be doing today, so y'all can follow along. You'll be uploading pictures into my hyperdoc, and that's what you'll be turning in for our notes for the day, which you would be doing in class. So verify the identity, the quantity of 1 minus tangent t squared is equal to secant squared t plus 2 times tangent of negative t. Okay, so we would need to verify the left-hand side is equal to the right-hand side. I want to know that 1 minus tangent t squared is equal to secant squared t plus 2 times tangent of negative t. So looking at this, I see that I have maybe a negative thing that I just talked about, but I usually want to start on the one where I can expand it out, where I can perform the squaring of it, foiling it out, whatever it is. Typically, those tend to pay off a little bit more than manipulating with this side. Anything that looks a little bit more complicated usually is the one I try to start with because I can do more stuff with it overall. So begin by squaring the left-hand side in hopes of using Pythagorean identity. So 1 minus tangent of t squared means that I'm going to multiply 1 minus tangent times 1 minus tangent. And when I do that, I'm only working with the left side. I'm not touching the right-hand side. I have 1 minus tangent times 1 minus tangent. If I FOIL that guy out, I get 1 times tangent minus tangent t plus tangent t squared, or simplified as 1 minus 2 times tangent of t plus tangent t squared. So that's if I just square this binomial and simplify it. So I kind of did 2 steps in one. I hope you don't mind. If you're confused about that, work it out. Completely FOIL the left-hand side out. So that's the first thing. And then I'm like, okay, so I have something to work with now. I have more stuff to work with. And I notice I kind of have 2 tangent t, and I see that that's part of this identity that I want to keep. Then I'm like, all right, I got 1 and tangent squared t. 1 and tangent squared can give me secant because of that Pythagorean identity. So if I write them next to each other, then I'll be able to easily identify it. So that's what I'm going to do next. I'm going to say, because it doesn't matter, they're being added and subtracted. Order doesn't matter here. 1 plus tangent squared t. I just moved this guy right over here. Minus 2 tangent t. Rewrote it. And now I'm going to use that Pythagorean identity. 1 plus tangent squared t is equal to secant squared. So secant squared of t minus 2 tangent of t is what I have, right? I'm saying that this is equal to this. That's my Pythagorean identity that I'm working with right now. And I got secant squared t minus 2 times tangent of negative t. So notice that I have a 1 negative here, a difference of sign here, and a negative here. This is what I'm talking about when I'm saying that sometimes we need the fact that it's off by a negative in the right spot for it to work to our advantage. So it looks like we're off by that negative sign. right here doesn't match. And then I got this weird guy. But remember, we just said that tangent is odd. So negative tangent of t, or like negative 2 tangent of t, is tangent of negative t, right? So I have negative tangent t, and I could rewrite that as positive tangent of negative t. I just got to keep the 2 on the outside. 2 times that stuff is happening. So we're going to rewrite secant squared t minus 2 tangent t as secant squared t, don't mess with that, as plus 2 times my negative tangent t. I'm substituting this guy in right here. So I end up getting secant squared t plus 2 times negative tangent t. Whew, that's a mouthful. We're using the fact that tangent is odd. And now, if I distribute this negative 2 times the negative tangent t, I end up with secant squared t plus 2 times tangent of negative t. Not distributing, I'm sorry. So substituting back in tangent of negative t is negative tan t. So negative tan t gives me the negative on the inside. So this can get a little tricky, right? Let's just recap really quick. So we were off by a negative sign. We were super close. We remember that negative tangent t equals tangent of negative t. Okay, I've got negative tangent t. So I'm here. I want to rewrite it and then substitute this guy in. So I'm here, right? Here is where I am. 2 times negative tangent t. That's the same thing as I was right here. I just rewrote it with a set of parentheses. And then substituted in this equation, substituted in this equality. So this parentheses is going to be replaced with negative t. And voila. I know that's actually kind of like really weird. But practice makes perfect. Also, I am working, you guys, on I got an iPad from the school. I am working on getting a thing where I can write it out with you guys. But I had a really hard time when I was doing the first couple of videos where I was video recording my hand from up above. And it just took a very long time to get that content onto YouTube. It took a really long time not to film it per se. It went by pretty quickly for the most part. But the process of just getting it online was a real pain. So I got an iPad from the school. I need to get one of the tech people to download this really cool app that will be like a whiteboard so I can write it out like live so you can see instead of just using slides. They're nice and clean, but I kind of want to do a hybrid of the two. You guys let me know what you like best. Do you like just the slides? Do you like it when I work it out with you? I like working it out because I can like write little side notes and stuff on the side that might be helpful for later on. Also, sometimes I have to skip steps because I can't fit as much on the slides here. Also, writing the math, it's not hard, it's just time consuming. And time is of the essence. So we did this first one. We used symmetry to verify an identity, and I think I gave you guys 3 homework problems to practice doing the same thing. So you will have to use the fact of symmetry to verify the identity 3 times. Mission accomplished. Feeling good here. So there's some guidelines for verifying identities that I wanted to reiterate because this stuff can be super challenging and like mentally taxing. These are just guidelines. As a general rule, only work on one side. Do not start manipulating both. You can get lost. It's very easy to get lost and confused on what you're doing. Plus, we can't even assume that an equation is true. So you can't just be like, oh, this must be true and start finagling on both sides. Properties of equality cannot be applied during this time. So just keep that in mind. You're proving that it's true or proving that it is not true. You can't just assume unless it's given to you that it is. We also are verifying the identity by changing the form of one side until we get to the other side. That's what I was saying when we either manipulate the left-hand side and get it to the right or start with the right-hand side and get it to look like the left-hand side. Like I was saying earlier, work with the harder side. It's easier to reduce and simplify versus starting from scratch or building some sort of function. Remember when last week when we were going over something that was equal to 1. We worked with the side that was not that had the trig functions on the left-hand side, I think it was, and ended up manipulating that until we got the number 1 versus starting with 1 and trying to work backwards. It would have been really, really difficult to do that. Not impossible, but difficult. Here's something like a pro tip. If an expression contains more than one term, combine them. So if you have like 2 fractions, get a common denominator and combine them. Oftentimes that can be helpful because this multiplication might be an identity that you can use, or you might be able to pull out something that they have in common and do something cool with it. So this could be like A over B plus C over D, or A over B minus C over D. This is very abstract, but it can be helpful to combine them. Not always, but sometimes. Also, if you're really stuck, convert everything back to sine and cosine. We know that sine and cosine obviously are in terms of sine and cosine. We can convert tangent into terms of sine and cosine. And if we can convert tangent into terms of sine and cosine, because cotangent's a reciprocal of that, I can do the same. Similarly with secant and cosecant. So sometimes just putting everything back in sine and cosine can be really, really helpful, especially when you're struggling or you're really stuck, because then you can work with just the 2 beasties. Also, apply algebra when appropriate. So if it looks like you can distribute something, try it. If it looks like you need to factor something, do it. If you need to factor something out, pull out a GCF, try it. If you need to multiply by a conjugate, heck, try it out. If you need to FOIL something, try it out, you know? You never know where it could lead with these tricky trig functions. And lastly, but the most important, is you have to know these fundamental identities. Like have to, inside out, upside down, backwards. They are the most important part. Obviously, like you guys should be pretty familiar with reciprocal identities now, ratio identities, and Pythagorean. But now we have a few wrenches in the mix with the symmetric identities as well. So use that. Like I said, this is just a note. There's no right or wrong place to start when working through trig proofs. I think about them in advance to show the nicest way to get there, but just because I started one way doesn't mean that the way that you're starting is incorrect. As long as you're adhering to correct substitutions and you're obeying all of the laws of the land, the math land, then you should be okay. Our paths can be different. There's no right place to start. It really just depends on the way that your brain works, and obviously all of us are different. I like to tell you guys to think on it. If you're stuck, that's okay. Give it a minute, think about it for a second, look at what you have, look at what you want to get to, see if there's some sort of connection somewhere. Just think on it, and try something. Don't be afraid to try something and see where it goes. It might be the greatest thing you ever thought of, and it might lead nowhere, unfortunately. But just sit and think on it. And also sometimes it's okay to take a break. They can get frustrating for sure. Yeah. Not all of your first attempts are going to lead to success. And believe me when I say that is me about 90% of the time. I really have to think about it because there's so many different manipulations that we can do. And especially once we start throwing in the double angle identities and things like that, it can get really tricky. But don't be, discouraged if the first attempt doesn't get you to the right answer. Like I said, just try something. Try substitution, try to simplify, try operation, see where it goes. Like I said, sometimes it's a dead end. That's quite all right. At least you're working, and at least you're trying to do something. You're strengthening your brain during that time. And if your mind can take it, try to think about why that failed. Think about why what you just tried got you nowhere. Try to identify exactly what that is, and that's actually going to strengthen your critical thinking skills as well, and your proof writing skills. Remember, you guys, we're in the learning pit right now, so it's going to be challenging before it gets easy. Some might come nice and quickly to our brains, but you're in the learning pit. Do not give up. Just keep going. The more you practice, the more comfortable you'll get. But don't expect it to be easy. Be prepared to be challenged in the best possible way. You guys are working through really tough problems, critically thinking, and strengthening your problem solving skills all in one. Also, dealing with trade, my fave. Last but not least, please don't give up. I know it can be super tempting and it can be very irritating, but I promise, stick with it. Ask for help, right? I'm big on collaboration. I want you guys to reach out to one another, although we might not be in the classroom. Reach out to your friends, call each other up, talk it through, talk it out like you would in class. You guys can, hit me up with any questions you guys might have. I have office hours where we can get together and talk about stuff too, because it can get really challenging. So with that being said, a little bit of hope here. Let's do example 2, verifying an identity. So we want to verify that sine squared theta times tangent squared theta is equal to tangent squared theta minus sine squared theta. So what I noticed right off the bat, these look almost exactly the same, except somehow there's magically a minus sign and they're separated. So I'm like, okay. Let's think about that. I need to keep the sine and the tangents, and I need to keep them squared. So how am I going to do this? I'm going to need to do some sort of manipulation. So our first step is, as a general rule, the side with more stuff is considered more complex. So we're going to start with the right-hand side. Like, notice this is just one expression and this is 2 of them. This is more complex, so we're going to start here. We're going to go right-hand side, prove it to the left-hand side. So I'm going to start with just having tangent squared minus sine squared. And I know that I can rewrite tangent in terms of sine and cosine. So this is all I'm doing, is I'm taking this right-hand side and substituting in tangent is sine over cosine, or since I have tangent squared, sine squared over cosine squared, and making that substitution. Now I'm going to work with this part here and continue on. I want to get sine squared times tangent. So I've got a minus sign here, and I've got sine squared theta over cosine squared theta minus sine squared theta. What I'm going to do here is kind of tricky. So this is going to seem kind of weird, but I'm going to break up this fraction. I'm going to break up sine squared theta divided by cosine squared theta. And the way I'm going to break it up is I'm going to say sine squared theta over 1 times 1 over cosine squared theta minus sine squared theta. So I'm going to break it up. I'm going to decompose that rational term. And the reason being is that 1 over cosine squared is secant squared. And I want to use that. And it might not seem apparent right now because I'm trying to get sine squared and tangent squared together, but that's what I'm gonna work through. So I'm gonna leave sine squared over 1 times this becomes secant squared, that's the substitution, minus sine squared. So now I have sine squared times secant squared minus sine squared theta. Now, big hint is when I have the squareds, I want to use those Pythagorean identities. I want to use them eventually. But before I can do that, I notice that this term has sine squared and so does this. And I notice that this side of the equation has sine squared multiplied by something. So that's what I'm going to do. Sine squared, I'm going to factor out a sine squared on both sides. So sine squared theta is equal to secant squared minus 1. Now, secant squared theta minus 1 is tangent squared. So if I substitute that in, I get sine squared theta times tangent squared theta by substituting in that Pythagorean identity. Now, this one, I'm feeling on fire. Pew, pew, pew. Pew, pew, pew. Hold up. Wait a minute. Verified identity. Okay, I gotta get off TikTok. But this one took me a while to ponder over and think about why I wanted to replace cosine squared with secant. I didn't really have a hard time breaking up the fraction because sometimes it's just good to decompose or put things together. But I really had to think about, why do I need secant squared? And the reason I need secant squared is because I need tangent squared, but I can't just convert this to one secant squared into 1 plus tangent squared. That wouldn't help me. I needed to get the opposite. So I needed to factor out this, guys. But like I said, with practice, you guys will get better. Promise. All right, a note. In the first step of example 2, the last one, we converted everything to sine and cosine. And then usually sometimes when this happens, since they're ratio identities, oftentimes we're going to end up with a compound fraction that we'll have to simplify in order, excuse me, I got the hiccups, in order to finish a proof. So something to keep in the back of your mind, sometimes we'll get a compound fraction to simplify in order to finish a proof. So for example, this was a complex fraction. I kind of broke it apart, then simplified it to finish the proof. Sometimes it might be a little bit crazier than that. So that's what I'm saying. Last example for the day, and this one is a little bit long, which is why I only wanted to cover 3 examples today. So verifying an identity by simplifying those compound fractions. So like I was saying, you're going to end up with a compound fraction. Sometimes we need to simplify them. And this one was really hard to fit on the screen. So bear with me. And some steps combine multiple steps in one. So I'll do my best to make sure that I point those multi-steps verbally. So make sure you got your eyes and ears peeled for this. So we want to verify that 1 over cotangent, or 1 plus cotangent divided by secant x plus cosecant x is equal to cosine x. So this I can see right away that I'm going to have to work with the left-hand side. The left-hand side is way more complex than the right-hand side. Shoot, the right-hand side is just cosine. All right, so we need to make this guy somehow get to cosine. So I'm just thinking out loud here. I'm like, okay, I can rewrite all of these in terms of sine and cosine. I'm going to do that because I need to eventually get them to cosine. And I know eventually down the road, I can use potentially Pythagorean identity to get everything combined, or it's just, it's just something to try right now. So you're going to start with the left-hand side, and we're going to use reciprocal and ratio identities to substitute in cotangent, secant, and cosecant. All right, all in terms of sine and cosine, because like I just have one cosine over here. So this involves 3 steps, right? This is the left-hand side. 1 plus cotangent x divided by secant x plus cosecant is going to be equal to 1 plus cosine over sine. This is substituting in cotangent, right? Secant is 1 over cosine, and cosecant is 1 over sine. So we substituted in 1, 2, 3 parts from this equation to this guy. And I'm pretty sure you guys are going to be okay with that. I don't think you guys will be fretting on that at all. But now we have a situation. We did something, but now we have a double-decker fraction. So the next thing we're going to want to do is multiply the numerator and denominator by cosine sine to get the least common denominator for all fractions. So since I have a broken fraction on the bottom, I need to get rid of that. So I have cosine x and sine x. If I multiply by cosine x and sine x on the bottom, whatever I have to do, I have to do the same thing to the top in order to get rid of the denominators on the bottom. The only way I'm going to get rid of cosine is multiply by cosine, right? And the only way I'm going to get rid of sine is multiplying by sine. So I have to multiply both pieces of this by cosine times sine in order to get rid of the denominators. Then I'll have stuff left in the numerators, and that's fine. But I have to get rid of the double-decker denominator on the bottom. So doing so, I have to distribute this 1 times cosine x sine x plus cosine x sine x times cosine x sine x, and the signs are going to cancel right here on the numerator. And then the denominator, 1 over cosine x times cosine sine is going to leave us with sine. 1 over sine x times cosine x sine x is going to leave us with cosine. I know that's kind of a lot, but let's simplify this guy out, right? So in my numerator, I'm going to have cosine sine, plus cosine times cosine, that's cosine squared, and then bottom is going to be sine plus cosine. Okay, just simplified that guy, and that was honestly, this part was really crazy. Doing the distribution wasn't as awful as it seems. It looks worse than it actually is. And then we ended up here. Okay, no more double-decker fraction. So we're in good terms, but I still need to get this whole thing to look like cosine. My goal, I remind myself all the time in the middle of the proofs, what is my goal? Because it's easy to get lost. So I'm looking at these cosine, sine, cosine, sine, cosine. What do I notice between this expression right here that I can do to start simplifying? Well, I notice I have cosine once here. I have cosine a second time here. And I have sine x plus cosine x. I notice that there's two cosines in the numerator, so you know what? I'm just going to try and factor out a cosine x. If I do that, I have cosine x times sine x plus cosine x, because it's cosine squared, over sine x plus cosine x. And well, would you look at that? The numerator and the denominator are going to cancel out. Because this is a product, I'm able to do that. If it was, or because this is a product, I'm able to do that. Also, because this quantity matches up exactly. You kind of have to be careful with this. You can't just have sine x on the bottom and then factor out and cancel out the sine x on the top. Be really, really careful about canceling out denominators. So those of you that have really struggled a little bit with canceling out things in algebra 2 or just regular algebra, be careful. Make sure that's a legal move. I am anticipating a lot of people messing up in this step. But doing this results in exactly what I wanted. Gives us cosine x. And we're done. Yeah, we're done. Woohoo! That one was kind of crazy. Minds are blown. All right. But not totally unattainable. Like I said, the hardest part of this one was multiplying to get rid of the denominators, to get rid of the double-decker fractions. That's our main issue here. Distributing looks ugly, wasn't that bad. Pulling something out, canceling out, not that bad. Just make sure you're not breaking any rules, right? So now your turn has come, my friends. All right, you're gonna get some practice in. I assigned you 3, 6, 9 problems, 3 of each type that we talked about today. It's due Sunday at 9 p.m. in your HyperDoc. And little note for you guys. P.S. I hold virtual office hours Fridays on Google Hangouts from 3 to 4 just for you guys. I don't have any other classes come in, and nobody came last Friday. It's okay. It wasn't mandatory. It's not going to be mandatory, but come with questions, or if you need help, that's a great time to do it. Especially while I'm there, it's before your homework is due. This stuff can be really challenging. We can just host, like, I don't anticipate like the whole class coming in there, but we can have one-on-one time. I'm sure if there's one of you with a question, there are others. Don't be afraid. This stuff can be really hard. It really can, but I know that you can do it. I'm here to support you guys in any way that I possibly can. You guys know that. I have your back through whatever is going on. But I know that you guys are super intelligent, and sometimes we just need another perspective. Sometimes we just need someone to lean on. Sometimes we just need another explanation than what's going on in our brains. So please, come to the Google Hangouts if you have questions on Friday. I hope to see you then. Alrighty? I hope you guys have a wonderful rest of your day. And never stop being awesome. Peace out. Or not. Did I end it? I don't think I did. Hold on. Yeah. Don't stop being awesome. Hang in there.